In the previous video, we learned about monoids, but in this video, we are going one step further. We are going to investigate groups. But what is a group? A group is simply a monoid that obeys the inverse law. This states that for every element A in a group, there exists an inverse of A, such that A composed with its inverse is equal to the identity element. But before we can see an example of a group, we need to take a look at truncations. We'll first consider what we refer to as propositional truncation. For example, the propositional truncation of the type A is a type with two constructors. Firstly, for every term in A, we have a term in the propositional truncation of A. Secondly, for every two terms in the truncation of A, we can construct a path between those terms. In other words, propositional truncation turns a type into a mere proposition. Similarly, we have what is called a set truncation. Set truncations are just like propositional truncations, except that they turn a type into a set. Note that for a set truncation, we use the subscript 0, and for a propositional truncation, we use the subscript -1. Using this notion of a set truncation, we can now construct a group. We'll start by constructing a loop space. But what is a loop space? Well, suppose we were given the type A and a term x in A. We define the loop space omega AX as being the equality type x equals x. For example, if A were the circle type and x were the term base, then omega of S1 base would be all the paths from base to itself. These would include reference, loop, loop of loop, the inverse of loop, and all the other paths that are homotopic to these paths. Finally, to turn a loop space into a group, we must first make sure that it is a set. We thus apply set truncation to fill any holes. In topology, this is called taking the fundamental group of a space. In our case, we are taking the fundamental group of a circle. But how do we know this is a group? Well, let's take another look at our definitions. Firstly, we need a set, but we already have a set since we applied seed truncation to the loop space. Secondly, we need to pick out an identity element in the set. Let's pick the term constructed from REFL. For the composition rule, we say that the term constructed from P composed with the term constructed from Q is equal to the term constructed from P composed with Q. And finally, we let the inverse of the term constructed from P be equal to the term constructed from the inverse of P. If we relabel these terms as numbers, then the composition rule corresponds to addition, and the inversion rule corresponds to negation. It now becomes clear that the group we have just defined is none other than the integers. We now know how to construct groups in Homotopy Type Theory. Thanks for watching.